So the video of the rocket sled from the U.S. Air Force with John Paul Stapp showed us that he went from rest to top speed in 5 seconds, and that top speed was 282 meters per second. And then he hit the water immediately after the rocket shuts off and went from top speed to a stop in 1.4 seconds. So because those are two different accelerations, we need to break this kinematics problem into two separate kinematics problems. So let's start out with part one. And as you can see, the rocket is going. So whenever we have a kinematics problem, it's connecting two different points, two different positions, two different times. So let's put a copy of our sled down here. Right, so that's going to be where we reach top speed. So let's now we want to, at each of these points, fill in all the information that we know. And so here's our starting point. That's our x naught. Now we're going to measure. We want to know how long the track is. So we can just refer everything to that starting point. So we can call our x naught 0. Right? There's no reason to choose anything else. That happens at time equals 0. Right? So our starting point is always time equals 0, or almost always. And then we have, well, what's our velocity at that point? Well, we're not explicitly given a number, but it says we start at rest. So that means that the velocity is 0 to start. Okay, so then over here at our ending point of this problem, we have our final position, which we don't know, and that's what we want to know. We have our time at that point, which is given as 5.00 seconds. And then we have our velocity at that point, which is given as 282 meters per second. And then we always have our acceleration, which I like to put in the middle because it applies to both parts. And so I'll put acceleration is equal to question mark. It's not given. And I put that in a dotted box because we're also not asked for it. Now, it might be interesting to know, but we're not asked for it. So that's a don't know and maybe we don't care, although we might have to find it out on our way to solving for the distance of track needed. Okay. Now, what I do know is that the velocity is going to be moving to the right the way I have this drawn. Now, you need to start, define what you call 0 and also define which way is positive. So it seems sensible to choose to the right to be positive. And because we're moving to the right and speeding up, that means our acceleration, I know, should be a positive value. Okay, I don't know what it is, but if I do calculate it, I know that I should get a positive number for that. Okay, so our target value is position. So we've got our two kinematic equations, and only one of those involves position, so I will go ahead and write that down. X equals x naught plus v naught t plus 1/2 a t squared. Right, and what you should always look at is, do I know everything? Right, so I don't know x, but that's my target, so that's okay. I do know x naught, I do know v naught, I do know t, but I don't know acceleration. Okay, so I can't use this equation yet. I need a little bit more information. So I go to my other kinematic equation, v is equal to v naught plus at. So that'll let me get the acceleration. I could possibly use this to calculate the acceleration that I need, and use that in the position equation. So now I look at this equation. Do I know everything other than acceleration? I know the final velocity, I know the initial velocity, and I know the time. So that means I can start working with this one. Okay, so I want to use this to calculate the acceleration, so I need to rearrange this, right? Resist the temptation to plug in what you know right now. It's going to be a lot easier to make sure you're doing the right thing if you do the algebra this way. So subtract v naught from both sides, so I've got v minus v naught is equal to at, and then I'm going to divide both sides by t so that I can get acceleration by itself, and that gives me acceleration is equal to v minus v naught over t. Hey, that should look familiar. That's just the definition of acceleration, which we're assuming in this problem is constant. Okay, so now this is a good time to plug in numbers, because when I plug in those numbers, I'll be able to calculate something right away, and I know what it represents. It represents the acceleration during this motion. So v is 282 meters per second, v naught is 0 meters per second, and then the time is 5.00 seconds. So that gives me an acceleration of 282 divided by 5, which gives me 56.4 meters per second squared. All right, so I'll put that in a dotted box. It's interesting, but it's not what we were looking for, but it is helpful. Now, as an aside, we can look at that. Is that a big acceleration? Well, what I would do is convert this to, the only acceleration I know anything about is the acceleration due to gravity. We experience what that feels like all the time, just sitting in your chair. So if I compare this to the acceleration due to gravity, which g is 9.8 meters per second squared, then a over g is going to give me, that's 5.8 g's. Right, so that's a pretty big acceleration. It's something that you might experience, or astronauts might experience. It's probably a little high for a roller coaster, but it's that's what we have to compare it to. So it's like 6 times the acceleration due to gravity. Okay, so back to our main problem, which is that I want to use this acceleration in the equation that's going to give us the displacement. So Now if I look at x equals x naught plus v naught t plus 1/2 a t squared, now if I look at that right-hand side, I know the values for all of those. So I can go ahead and calculate. So let's do that. Well, x naught is 0, right? And sometimes I'll just go ahead and I like to put a slash through terms where something is 0, or you can just write it down. And then v naught is 0, so that takes the whole term out, right? If you multiply 0 by anything, it takes the whole term out. A lot of times I see people make the mistake of saying, well, v naught, I cross that out, they forget to get rid of the t. So don't forget that. So that is 0, and then we're going to have a 1/2. So the acceleration is, need to use the value in meters per second squared, 56.4 meters per second squared, times the time, which is 5.00 seconds quantity squared. Now, a lot of times people will forget this square, just they forget to copy it down. If you write your units down, you won't forget, because I need to get meters, right? Every term in this equation has to have meters. So meters per second squared times seconds squared, that's going to cancel out the seconds and just give me meters. Okay, and so as I plug those numbers in, I get that this distance is 705 meters. Okay, so that's the distance, that's the length of track needed for the speeding up portion.
You asked me if an ordinary person, by studying hard, would get to be able to imagine these things like I imagine. Of course, I was an ordinary person who studied hard. There's no miracle people.
Now we're ready to do the second part of the problem, which is the slowing down part. So this, I've tried to draw the rocket sled getting hit by, or running into the water here. And so then, again, we have our two positions, right? So where you first hit the water and then where you come to a stop. And again, we're trying to find the length of the track necessary. And so we've got our 2 points here. Now, since this is a new part of the problem, the easiest thing to do is just to call this t equals 0. And so then this is going to be the time is equal to 1.4 seconds. Right? We were told in the problem that it takes 1.4 seconds to come to a stop once it hits the water. We know that the initial velocity here is the top speed, so it starts at 282 meters per second. Now, the question of what you want to call your x naught here, this is up to you. You could just say, okay, this is a whole new problem. I'm going to call this x naught equals 0. And then when you get this the displacement from this problem, add it to what you had before. Or you could say, hey, let's connect this back to the previous part of the problem. And that's what I'm going to do. So it's 705 meters from where it started, right? That's the value that we got from the previous part of the problem. Right, and just to keep from having to use all different types of variables, again, I'm just starting over here using the same sets of variables. I don't need new labels. Okay, so I know everything about what's happening at the starting. Now, the final velocity, this is one of those key phrases here where it says it comes to a stop, so I know that my final velocity is going to be 0. The final position is what I want to know, so that's x equals question mark, and I put that in a box. And the acceleration, which applies to this whole part of the problem, again, I don't know what it is. Well, I should have, again, define my positive direction, which is to the right. So I don't know what my acceleration is, but I do know that it's going to point to the left, right? Because we have a positive velocity and we're slowing down. The force of the water is going to point to the left. So the acceleration, when I calculate it, is going to be negative. Now, again, that's a don't know and maybe don't care about, but as you probably can guess, again, we're going to have to find the acceleration as an intermediate step in this problem again. Okay, so this is what I call focusing the problem, right? You've got your picture with your 2 points. All 7 variables are either labeled with a value or labeled as a target or labeled as an unknown, possibly don't care about. Okay, again, just to get the practice down, right, I can say, well, I'm looking for a displacement. So I eventually want to use the displacement kinematic equation, but I don't know the acceleration. So same situation, I'll go back to my kinematic equation for the acceleration. Now, the nice thing about the fact that I did the algebra without putting in numbers at the beginning is I'm doing the same sort of procedure again. So I can say, well, I know that my acceleration, I can just reuse that work that I did on the algebra. I know that acceleration is going to end up being the solution to this equation. Right? Now, plugging in values. Now, it's important to remember which one is the final velocity. Now the final velocity is 0 meters per second. The initial velocity is 282 meters per second. And the time is 1.4 seconds. Okay, so 0 minus 282, that's a negative number. And when I divide by 1.4, I get that the acceleration is equal to negative 201 meters per second squared. I put that in my dotted box because it's interesting, but it's not what the problem was asking for. And just to, again, compare, this is basically 20 Gs. Wow. Right, so most people black out at 10 Gs or less. That's why Air Force pilots nowadays wear flight suits that keep all the blood from flowing out of their brain when they experience extreme Gs. So 20 Gs is really, really rough, but turns out you can survive it, or at least a lot of people can. Okay, so now we want to use that acceleration we calculated. Again, the minus sign is important. We need to stay consistent with the directions that are in our picture. And now I can use that in my position equation. So x equals x naught plus v naught t plus 1/2 at squared. I'm just copying it down. So I decided to call my initial position the 705 meters that I'd already traveled with the rocket on, plus the initial velocity, that's 282 meters per second, times the time, which is 1.4 seconds, and then plus 1/2. So again, remember that's a negative 201 meters per second squared times 1.4 seconds quantity squared. So again, I'll just calculate what each of these is, plus 282 times 1.4. That gives me a value of 395 meters. And that's the distance that the sled would have traveled if you had just turned off the rocket but hadn't hit the brakes, hadn't used the water to slow it down. And so then we have a next one that's minus 197 meters. Okay, so that's the quote, I call it the quote unquote extra distance that you travel because of the acceleration, but since it's slowing down, it's a negative number. You don't go as far. So we add these up. That gives us the total length of the track, which is 903 meters. So if we look at just these two terms, that would give us, that's the length of the track where there's water. Right, so if you had decided to call your x naught equal to 0, you would have found just that value, which is 198 meters. And then when you add that to the 705 from the previous part of the problem, you would get the 903 meters for the total length of the track. And so this is why people will ask me, well, which one should I use? It doesn't matter. You just have to be clear at the end of saying which length are you talking about. So this is the length of the whole track. And if you're actually building this track, both of these values are important. Right? You'd have to say, okay, build me a track with a length of 903 meters, and then when you put the water out, put it in the last 198 meters. Right? So both of these are important, and that's why when you would communicate this result, you wouldn't just write down variables, you would use words.